Speed-wise?
It's coming down slowly, but
Okay.
not quite fast enough. Always worrying things will go back up as they reopen. But it's reasonably good now. Relatively low.
Yes. So can you allow me to share the screen?
Yes.
I'm still stuck here.
Yes, I thought you were already co-host.
I don't know. It says the
yes,
host is activated. I'm co-host now. Yes, good.
Yes, now you should be able to share the screen.
Okay, let me remove that and that and that. Okay, so that should be that one. Yes. Yes.
Okay, we'll start the recording. As before, if you do not wish to be seen or heard in the recording, then turn off your camera and microphone. And
Just
okay, and we will start again.
sorry.
We will start in a minute. So, everything okay, Pierre?
Yeah, it's fine. Yeah, just close the shutters because the sun is going. Too much sun.
Okay, so yes, okay, so we have Pierre's second talk. Just a couple of small announcements. So, as noted, there will also be another discussion session tomorrow at this time, and then the third talk will be on Thursday. If you have any questions related to the course or anything else related to OOPS, we also have a Discord forum, and there is a link on the website, and you can always ask questions there outside of the lecture times, and people will be looking there. So, okay, so Pierre, please, floor is yours.
Okay, thank you very much, Omer. So let's just summarize quickly yesterday's lecture. So we first looked at polyurn, which is a process where you have an urn with balls of two colors, and every time you pick a ball at random and you put it back along with a ball of the same color. And so, as many of you know, so the limit distribution for that process is a beta distribution. So, by which I mean that the proportion of green balls will converge to a random variable, which has beta distribution, and conditionally on that limit proportion, the urn is an IID sequence of Bernoulli rows with that limit probability. So that's the definitive theorem. And so then during the second part on that polyurn, I explained how using Bayesian statistics you could find the limit measure for that urn, so namely the beta distribution. And then I went on to do the same computation for the edge reinforced random walk, and so we hadn't completely finished, so I'm going to go there. So let me just mention first that so in the case, I had a very interesting discussion session, and so one of the remarks that was made so by Leo is that so in the computation I do in these two slides here. So by the way, note that there are always some typos in in my slides. So I have updated them. So they are now on the website, and I update them during during this course. So and so he noted that the computation on these 3 pages that you see here are, in the case where A and B are integers, they correspond to the proof of the de Moivre-Laplace asymptotics for the binomial distribution. So but here we assume that A and B are not integers. So note that so there are many ways in which you could find these limit distributions. I just wanted to emphasize a particular technique. And so the next thing we did was to introduce the edge reinforcement walk, which is a walk on a discrete, non-oriented, locally finite graphs. And so it's defined as follows. So you and it starts from a fixed site I0, which will matter because it's a non-Markov process. And at any time step, it goes it crosses an edge with a probability which is proportional to the number of past crossings of that edge. And so with the convention that at time 0, the crossings of edge E is given by AE. And AE doesn't have to be an integer. It could be any positive real. And then so we computed, so we noted that this process is partially exchangeable. And actually we got even more. We got a beautiful formula for the probability of that of a path, so which is this one. So this formula you can rewrite as gamma of I0A over gamma of J0 alpha. So note that in yesterday's talks, at some point I permuted the two. So the reason is that somehow I would like to have gamma of I0A as the normalization. So here it won't be the normalization of the measure. It would be actually 1 over the normalization. I wanted to be consistent, on the other hand, with the notation we had in the paper with Christophe Sabot, which is on archive. So I will stick to that notation so that you can follow more easily later on when I discuss star edge reinforcement on the MOOC. And so we have that computation of the probability of the annealed path. So the probability of the path, a certain path for the edge reinforcement homologue. So it can be written as a quotient of 2 quantities. So one depending on the final site, GA naught, and the final edge weight configuration alpha, and the other depending on initial site I0 and initial weight configuration A. And then we used that trick so that so if we compute the probability that so because this process is partially exchangeable, then it is a mixture of a reversible Markov chain because it's reversibly exchangeable. And then by the theorem of Coppersmith and Diaconis, of Diaconis and Friedman, we know that it is actually a mixture of Markov chains, of reversible Markov chains. And so now the way in which we are going to find the limit measure, so which we started last time, was by confronting the two approaches. So on the one hand, the annealed approach, the fact that you can compute the annealed probability of a path, so it's given by this quotient formula that I just mentioned. And on the other hand, the fact that the probability, so you can also compute the quench probability, and then by that confrontation, you get that the conditional probability that the limit x is in between x and x plus dx, condition on the path of a certain path, so I0 up to I0 equal to J0. So this is the former density phi I0A of x multiplied by the quench probability of the path, product of xa, xe to the ne for the edges e, divided by product of xi to the vi minus delta J0 of I. So where ne is the number of crossings of the edges, the edge E, and VI is the number of visits to I by that path, and then divided by the Anneal probability. So we got that formula, and that formula, here I'm rewriting it in the following way, which you can see at the end here, as first, so phi I0A of x divided by gamma I0A, and then a quotient of two quantities. So one at the initial point, so the product of xe to the ae over xi to the ai minus delta I0 of I divided by 2, and the exactly same quantity, but taken with the updated weights and the updated starting site J naught. Just after that, so we have the quotient of those two quantities multiplied by also the quotient of gamma J0 alpha and gamma I0 alpha. So we get that formula. So note that here we use the following equality identity, which enables us to write Vi minus delta J0 of I as a difference. So as you can see here in the middle of your screen. So, okay, so that's where we were yesterday. So then I mentioned quickly, so I will that you can do some asymptotic. So it's the same spirit, it's just a little bit more involved. So you start with Stirling's approximation. So I think Leo told me that actually the first one to do it was Demoivre, if I'm right. So you get that formula. And then, so you define that function, eta beta of y, which is a product of y e to the beta e over product over I of y I to the beta I over 2. And so that quantity, it will be it will be only not be small around the value of beta. So basically it will concentrate, the measure here on eta beta will concentrate around the value beta, and we'll have Gaussian approximation. So we do exactly the same trick as last time. So, and here you see a formula. So the phi I0A over gamma I0A multiplied by the product here. So all these, so these terms only start, so only depend on I0 and A. And then you let beta go to X. So you fix a certain X. You let beta go to X, and n goes to infinity. So n is here the sum of the alpha e's. So what you have to understand is that the eta beta of y over eta beta of beta to the n, again, so it will only be not small when y is very close to x. And for that reason, so all the terms here that you can see on the bottom, like for instance, ye to the ae, xe to the minus 1/2, so it will converge to xe to the ae minus 1/2 on the somehow set that matters when you want to integrate. So here and here the y similarly the yj0 over xj0 will converge to 1 on the set on which you concentrate and which your measure will concentrate. So in summary, you will have that. So now that Gaussian approximation I talked about. So here I'm writing q beta, which is quadratic potential. So you can write it as the sum of beta ij omega yij over beta ij minus yi over beta I squared. So the integral of the Gaussian integral here so has this explicit formula, and you can ask me in the discussion session on how to prove it. So it's actually proved in a more general case in our paper with Christophe, but I wrote down a proof, a shorter proof in that so reversible case. And so now so you simply use so that Gaussian approximation along with the formula on the bottom I'm showing here, and you obtain that one again, which is the limit of the integral of phi j0 alpha of y so dy. So note that here beta is alpha over n. And so obviously one is equal to that limit because it's equal to each of them. It's simply the fact that so the phi's here are densities of probability measures. So one is equal to that limit. And on the other hand, so using that Gaussian approximation, when beta goes to x, so the measure will concentrate against around x and will be Gaussian around x. You obtain that formula. So it's, I leave it to you as an exercise. So it's a more involved exercise than yesterday, but so it's exactly the same spirit. So and then we obtain that limit measure. So the important thing to notice here is that that measure has a memory of the starting site. So the starting site I0 appears here in the measure. It's with the term square root of x I0. So here I'm writing it a slightly different way than yesterday. So I'm writing the density instead of taking the bug measure on sum of xe equal to 1, I take the measure on the products of e different from a certain vertex, arbitrary vertex E0. So again, it's to be in order to be more consistent with the notation in our paper. And so now let me make a few remarks. So the most important remark here is that so this technique that I'm presenting here is new. So the approach for finding the limit measure is new, and the reason for that is the way so the initial result was obtained by Keane and Rollers, but actually, so after Coppersmith and Diaconis found it, but never published it. But I believe they did the same proof, as far as I know, is to compute the probability of a path. So as we did, to note that it only depends on the local time. So by local time, I mean the crossings of edges, and then to compute the probability of reaching a certain vertex J0 and a certain local time NE. So by which I mean that basically you fix a certain local time you want to reach, or an interval of local time you want to reach, and you compute the probability to reach that. So you have to sum over all possible paths. That gives you that probability. So you have to sum that Anneal probability over a lot of paths, and then you get an approximation. And that approximation, when you want to know whether the renormalized local time will converge, the probability that the renormalized local time will converge to a certain quantity, it will be on a certain interval, you'll have again a Gaussian approximation which appears, and you can conclude that like that. But it's a different technique. So let me note that that technique by Keane and Rollers, and probably by Coppersmith and Diaconis, has some advantages. So one advantage is that you get an interpretation of the spanning trees. So here I wrote that kind of mysterious formula that you have a square root of d of x, where so d is a principal minor, and it's also the sum of a spanning trees of the product for edges E in that spanning tree of the edge weights YE. So the final one. So so that formula is a little bit mysterious, and so in that paper of Keenan and Wallace, which I encourage you to read, they have an interpretation in terms of last exit trees of the work, but it could be also first exit tree by reversibility, and so this connects with another paper that I will try to find time to talk about, a very interesting paper of Angel, Crawford, and Kozma, where they find they prove the recurrence of edge reinforcement and work for strong reinforcement without using any of those limiting measures I'm describing in this course. But they use precisely the first exit tree of the work. So, okay, so that's for that computation of the limiting measure. So now, next question is, okay, so I started by assuming that the limit measure would have a smooth density, but what if not? So how can I conclude from what I did? So let me point out quickly the technique by which, one technique by which we conclude. Actually, I will give you two, but one we'll need some assumption first. So the technique I'm explaining now here is the one again which is outlined in that paper with Christophe on archive on the star edge reinforcement work. So it is as follows. So you take a smooth function on L1 on the simplex of sum one. So here. You assume that smooth function has empty intersection with any of the xe equal to 0 to avoid any embarrassment, any problem of convergence. And then you take here your putative limit measure mu I alpha. And you, so by mu alpha, here I mean the one with the density, which is written here. So that one. So I integrate my test function against that. So I get a certain function psi, which depends on I and alpha of phi. Okay. And what I want to prove is that for all those choices of alpha and I have that the expectation, so again, against my probability measure here, so I0 alpha of the phi of the random variable y, where y is the limit, is that integral psi of I0 alpha. So the way I proceed is in two steps. So the first step, we say, okay, so we note that the process of the position plus the edge visits, edge crossings, the vector of edge crossings for each E is a Markov process. With that generator, so here so with that generator, which is LG of I alpha, which is the sum of alpha ij over alpha I. So your label, alpha ij over alpha I, so gives the probability to go from I to j. And when you go from I to j, indeed, then you have to add to alpha the Dirac mass at 1, you have to add to alpha to the ij coordinate of alpha. So here it should be ij there shouldn't be any parentheses. So you should add 1 at the coordinate ij. So that's why your generator is like that. And then a good exercise is to show that for that function psi, that integral psi, which depends on I alpha, that generator applied at psi is 0. So in other hands, in other words, we'll have a martingale. So it means that psi of xn z of n of phi will be a martingale. So actually the proof that of the fact that this psi of xn zn is a martingale is very close to the it uses really similar ingredients to the proof that of the first part of the functional equality we wrote. Let me show it out, point it out. It's very similar to the proof of that functional equality. It uses similar ingredients. So, and then once we know that psi of xn z of n is a martingale, so we can write that psi of I0 alpha is the expectation of psi of xn z of n. But now psi of xn z of n again, it will be the integral against something that concentrates around the limit of Zn over n. And therefore, we can show that it will converge to phi of y when y is the limit of z of n over n. So again, so now this proof is similar. Not exactly the same, but similar to the second part where we were finding using the normalization, using that the integral of all those measures we are taking is 1 to conclude for the exact form of the density. So that's one way to proceed. Now another way to proceed, which is nicer, is to assume that your limit measure here that I gave you is a probability measure. So if you know that, and we know now that there are various ways to show it. So because it's so in particular by supersymmetry, you can prove that it's a probability measure. But so Andrew Swan would be able to talk much more about that than me, so you could assume that. So let's assume that. So then, so how will the reasoning go? So we sample x. So the limit x, the limit proportion of this. So x here is a vector. So it's the vector of xe. Where e's are edges, and the sum of xe is 1, and we sample the x according to again the formula we have here, we have been given here, and then we compute the probability of a path I0 up to in plus 1, so not in, you'll see in a minute why, conditional in an x. And you get that formula. So this is a formula for the Anneal probability, right? Sorry, the quench probability, because it's conditioned on x. Now you want to anneal, so you want to integrate over that. So you get another formula, so C gamma of I0A multiplied by, so I shouldn't have actually put the C gamma over I0A because it's part of the mu I0A, okay? But, so it's C gamma of I0A multiplied by that quench, integral of that quench probability against the density measure, against the Lebesgue measure. And then you get that because you know, so that you can compute explicitly that integral. The reason why you can compute explicitly that integral is that when you multiply xc by when you multiply x by xc to the ne here and by xi to the vi by those products, actually you get using that the integral of that quantity here. So that integral is 1. You get actually a term which would be proportional to gamma at the new configuration of edges with the new starting point in plus 1. So you can compute it, and so you get that expression. And then you can compute.
You add to in Kronecker delta, but in is not a number. Last formula.
Which formula?
Last.
Yeah, exactly. So it's here there is a typo. So it should be so let me see, but I haven't explained the last formula. So let me explain it. And so then you compute the conditional probability of the path I0 up to in plus 1, knowing I0 up to in. So then you would go get a quotient, which would be gamma of in configuration at
in plus Kronecker symbol. What does it mean?
Let me finish, and let me finish, and then so this conditional probability of I0 in plus 1 knowing I0 in, it's a quotient of the two probabilities of a path I0 in plus 1 and the path I0 in. And so therefore you can write it as gamma of in configuration of edges at time n divided by gamma in plus 1 configuration of edges at time alpha. So here what I wanted to point out, but indeed there is a typo, is that so it should be then the gamma of in and comma alpha plus the Dirac mass at the edge in plus 1, that which we will cross next time. Okay, and so this quotient is actually alpha in plus 1 over alpha in. So is it clear now?
No, thank you. No, in is a number or it's a point? What does the in plus numbers, plus symbol?
So here there is a typo. Instead of having gamma in plus delta in plus 1 alpha, it should be gamma of in alpha plus Dirac at delta at in plus 1. So which means that at the edge in plus 1, you add 1, okay, to the weight. Okay.
Thank you.
So that's the typo. So thanks for pointing it out. So that gives that formula. And then so you see this is the formula for the edge reinforcement homework. So you can say this process, because I can compute all the conditional probabilities. So and they are the ones of the edge reinforcement homework. This process has to be the edge reinforcement homework. But for that you have to assume you have a probability measure. Okay, so now I'm going to continue in two directions. So first, I will explain rapidly the results which were obtained beforehand. So in particular by Pimentel, Robin Pimentel and Trees, and by Merkel and Rollers. And then I will explain our new approach with Christophe Sabot. Which goes in particular through a link between the edge reinforcement homework and the vertex reinforcement process. So again, so we have already explained that using partial exchangeability, the edge reinforcement homework is a random walk in a random environment. We have just computed the limiting measure, so which was first done by Coppersmith, Diaconis, Keane, and Rollers. Okay, now. Robin Pimentel, so in his PhD, looked at the case of trees. So that case is special for the following reason. So let's, for convenience, root the tree at the initial site, I0. Now you note that because it is a tree between two visits at each vertex, once an edge is crossed, you have to come back through the same edge because you cannot do any loop. So it's trivial. And then because of that, independently at each vertex, you have a process where basically every time you cross an edge, you will add a label of 2 to that edge. So in other words, it would be a polyar urn where you add 2 balls every time you pick a ball of a certain color. But writing it like that is the same as actually if you divide in the probability everything by 2 is the same as starting from weights which are divided by 2. So that's what I write here. And note that so the initial configuration you have on the weights of edges is changed at the edge which is I0j, where j is the father of I0, because when you arrive at I, you will have to have gone through j, and therefore so your weight here will have been increased by 1. So now that environment is independent. So you have those polyar urns which are independent, and therefore, and now a generalization of the statement with 2 colors as I stated at the beginning of the first lecture is that so the limiting environment here is Dirichlet. So which is generalization of beta distribution. And therefore, we have a random walk in independent Dirichlet environment. And so using that, so using the powerful techniques from random walks and in random environment, and also adding some, so it is actually quite a significant paper. So Robin Pimentel proved a recurrence transient phase transition. So he showed that for strong reinforcement, you have recurrence. For weak reinforcement, you have transients, and he exactly showed the phase transition. And now Merkel and Rollers, so over a period of 10-15 years, worked on the question of graphs with loops. So they started with the ladder, and then they improved their technique, and they proved the recurrence on the 2-dimensional graph. So which was not Z2, it was Z2 where each edge is replaced by a large number of edges. So they used a Mermin-Wagner type argument. So that was the mainly, so these are the results which were obtained before we worked on it. And so with Christophe Sabot, we introduced a link with statistical physics, which goes through another process. So that other process is called the vertex reinforcement process. It's defined as follows. So now you give yourself some conductances, WE, on the edges. So WE, E in E. Your process YS has a memory of the local time. So the local time here is Lj of S. So this is 1 plus the time. So you spend in J up to time S. So in other words, this is a local time at J with a convention that we start with a local time, which is 1. So the vertex reinforcement process is defined as follows. So so conditionally in the past, you jump from I to a neighbor J at a rate which is proportional to that local time. So which is Wij Lj of S, where J is the local time at J. Lj is the local time at J. So if you look at that process, initially, the local time, so you sit on your vertex I0, the local time at your neighbors won't change because you sit at I0. But once you move, the local time that you will have spent at I0 will matter for the future of the process. So it was initially proposed by Werner, and ironically, it was actually suggested as a kind of a continuous time version of the vertex reinforced random walk, so which displays a completely different structure, and in particular, which localizes, not in the sense of statistical physics, but it actually really, the process really localizes on a small number of vertices. So, for instance, I proved during my PhD that on Z, it localizes on 5 vertices. And Davis and Volkov did the first study on trees, and in particular, they found the limiting measure on trees. So now, why am I introducing that process in the context of edge-reinforced random walk? Is because you can rewrite the edge-reinforced random walk as a mixture of that process, of that vertex-reinforced jump process. So, so let me state the theorem. So you take an edge-reinforced random walk with weights alpha e, initial weights alpha e. And so I'm claiming here that you can rewrite that process as a mixture of vertex-reinforced jump processes with conductances WE distributed as independent gamma random variables with parameter alpha e. So here I'm comparing a discrete time process with a continuous time process. So the way I do it is I compare them at jump times. So I compare the path, the trace, so at those jump times. So this result was proved. So first, actually, okay. So it somehow. So this equivalence here applies to actually any linearly reinforced random walk, and so it was the version that was first proved was actually by myself for the vertex reinforced random walk in a survey on reinforced random walks, which is on arXiv, which has been published in 2011. But so I'll explain at the end of the talk that there was a catch that so I didn't see at that time for the edge reinforced random walk. So let me so first so let me prove that theorem quickly. So it's based on the following idea, so which is a nice idea by Herman Rubin, which goes as follows. So you know that if you take a Markov process, let's say you take a process in environment XE, right? So where X is the XEs are on the edges, are fixed. So you go from I to J with a probability which is Xij over the sum of Xij for J adjacent to I. So this is a Markov chain. It's a discrete Markov chain, but you can again write a continuous time version where you take some timelines. So at each edge, with so alarm probability, so where alarm rings on intervals which are spaced by exponential random variables of parameters xe, and then so simply you run the process. So you run the time clocks only when you are adjacent to E. So now we are going to do the same thing for the edge reinforced random walk. So the difference is that the weights, so which are the AE of the ZE of n, the weights are updated. So we start the first time. First let's say we are running. The process is adjacent to a certain E. So then you have your clock which runs, and it waits for an exponential time of parameter AE, which is the initial weight. So once you reach that time, that exponential time, so but which may not be at the first visit to let's say, so if E is ij, it may not be at the first visit to I, it could be later on. But when you do that, then you cross the edge ij, and therefore you update your weight by 1. So you add 1 to your weight. So on the other word, in other words, so we have the following structure that we can write a collection of IID random variables, which are exponentially distributed with parameter 1. And then so for every edge E, we run that timeline where we have alarms which are spaced by exponential of parameter alpha E plus I variable, independent random variable. And then so basically you are equipped with all these timelines for each edge E, and now you define your process as follows. So the clock only runs, the clock of a certain edge only runs when you're adjacent to that edge. And then as I said, so you wait for that exponential time, and when at which the alarm rings, when the alarm rings, you traverse the edge, and you can show by two properties of exponential. So first, the memoryless property of exponential, and by the fact that the probability that the exponential of a parameter A be smaller than the exponential of a parameter B independent is equal to A over A plus B. So you can show that those two processes are the same way you would do it for Markov processing. So you have this link now. So we have, out of the edge reinforcement homework, created a continuous time process. So which is run as I just explained. So now let's focus on a particular timeline. So we fix a certain E, and we look. So what do we have on that timeline? So the first exponential is of parameter AE. The second exponential is alpha E. So the second is alpha exponential of parameter alpha E plus 1. The third is exponential of alpha E plus 2, and so on. And now, so this process actually is known. So this point process is known, is actually a Yule process. And by a result of Kendall, you can rewrite that process as, after an exponential change of time, as a Poisson point process with constant intensity, constant random intensity WE. So, but here I'm going to claim it in a different way. So I won't do the time change. So I will keep the same time. So therefore, I will have actually a probability of an alarm between time t and t plus dt, which will be WE multiplied by e to the t dt. So which increases exponentially with the time. So the statement of the result by Kendall is that there exists a random variable WE, which is gamma distributed with parameter alpha E, such that conditionally on that value WE, you have a Poisson point process with exponentially increasing intensity WE e to the t dt. And then so now you're almost done. So you just conclude by noticing, making the very simple remark that you can compute easily the time you spent adjacent to E. So the time you spent adjacent to E is simply the time you spent, if E is ij, is simply the time you spent at I plus the time you spent at j. So therefore, your process goes from so x to y at a rate which is wxy e to the tx plus ty, where t is a local time, tx is a local time at x. But now, when you arrive at that stage, you think, okay, now I have indeed made a link between the edge reinforced random walk and an exponentially interacting random walk. So which is with rate wxy e to the tx plus ty dt. So, but actually now you can notice here the dt here, you are at x here when you write that rate. So it's actually dtx. But now e to the tx dtx is also the differential of e to the tx. So if you change the times at all sites, so you know there is no reason why you should impose yourself a certain time scale at each vertex. You could change the time scales, and so you change them by exponential order. So you define Lz, which is e to the tz, and so then you get actually a jump rate which is linear. So it's fascinating at first sight that the process with exponentially interacting, after rescaling it, is actually linearly interacting. So it means that somehow the function does not tell you everything about the process. So the rate function. So you have to somehow some classes of functions give exactly the same process. And that's the part actually. So I hadn't anticipated before we worked with Christophe. And so again, so I looked at it from only a timeline point of view for the vertex reinforced random walk. So in order to prove that conjecture on the 5 points, so to give a short proof of that conjecture of the 5 points. So in that way. So so now I've given you now two out of that process. So that vertex reinforced jump process, I've given you two ways, so two jump rates. So one is wij lj, and another one is when you take, so you rescale the local time so by li equal to e to the ti is wij e to the ti plus tj. But now I want actually to introduce yet another time scale in which I will have the following jump rate, which is 1/2 of wij, 1 square root of 1 plus lj over 1 plus li. So the reason why I want to have that jump rate is that actually it is the exchangeable time scale. So it's the time scale in which the walk, the vertex reinforced jump process, is exchangeable. So it's not surprising that the vertex reinforced jump process should be exchangeable in a certain time scale, because you know that the edge reinforced random walk is exchangeable, and you know also that the edge reinforced random walk is a mixture of vertex reinforced jump process. So now, so what is that time scale? So here's the first one we already wrote, is Lj equal to e to the tj. So the second time scale is curly Lj equal to Lj squared minus 1, which slows down the process. And then you have those jump rates, so you just compute them. And you see that, so, you know, if the quotients of local times converge, indeed, you see a convergence towards the Markov process. But actually, you will have more, because you'll have, by partial exchangeability, that the process conditionally on the limit is a Markov jump process. Okay, so that's a remark I wanted to make. Okay, now what do we know about the VRJP? So first, we know that the edge reinforced random walk is a mixture of VRJPs with random conductances, WE, independently distributed at gamma random variables with parameter alpha E. We also know that this process we could write, so you know, the three processes I wrote here in that slide, they actually define the same process, just with a change of time. Okay, so now another remark I wanted to make, which will be useful when we'll try to implement the Bayesian approach for the vertex reinforced jump process, is a question of conditioning the VRJP So I will take the x here. So the x is actually the last one in the slide. So it's the exchangeable one, the one in the exchangeable time scale. So the x condition on a path up to time t with a certain local time s and n position j naught. It can be rewritten after a certain time change at a VRJP with a starting point j naught and weights wij s to the power of s, so exponent s, which is wij square root of 1 plus si square root of 1 plus sj. And the times change you have to do is first you subtract the local time si to the time at I, and you divide the whole by 1 plus si. So it's a simple computation, so I will let you do it. So it's explained here at the end of the slide. So this computation is important because it will allow you to have that Bayesian structure that, if you condition the vertex reinforced jump process on a certain path, you still get a vertex reinforced jump process after that small changes. So now, next thing I want to explain is the probability, how to compute the probability of a given path. So the reason I want to do it is exactly, again, the Bayesian statistics approach to find the limiting measure. So how do you find the limiting measure? You will compare the Anneal probability of a path to the quenched one. So let's start by the Anneal probability of a path. So we use the following notation. So I0 arrow I1 with V0 above the arrow, etc., up to Vn minus 1 In, which is J0, and then T. And so this notation will use to denote the event that at time T, the walk will span the time between V0 and V0 plus dV0 at time at site I0, then it will jump to V1, span again time between V1 and V1 plus dV1, etc., until it jumps at In, and at In it will span the rest of the time until time T. So T is the total time. And SI here, so we will define SI as the total time spent at vertex I at the time T. So now we have the following formula that the Anneal probability, so starting from I0 and with edge weights W of a path, can be written as this quotient of exponential, so exponential of minus sum of over the edges of wij square root of 1 plus si square root of 1 plus sj minus 1 divided by the product for I different from j naught. So j naught is the endpoint of square root of 1 plus si, and then multiply by the product of ik plus 2, ik plus 1 over 2, multiplied by dvik. So let me explain quickly how it is done. So this way of computing was first done in a paper with Christophe again on which is called inverting Reinhardt, and it just published in PTRF in 2016. And so the idea is as follows. So you want to compute a probability of a path. So you have to separate into two parts. So you have to separate into the holding probability. So every time you are somewhere, the probability is that you don't move. And actually that holding probability will give the exponential term here on the numerator. And then you compute the jump probability. So which will give you the 1 over the product of square root of 1 plus si. multiplied by the product of the W ik plus 1 over 2 dvi. So, so let me quickly sketch how it's proved, and I will finish by that. So you define that function, that quadratic function f of psi, it's sum of wij, psi I, psi j. So I'll come back to gi later. So I don't need gi right now. So and let me give a slightly different argument than the one on the slide. So let's look at, so instead, so I know that we want to compute actually in the exchangeable timescale, but what I'm going to explain now for the holding probability is easier to understand in the linear timescale. So when you are at I, between time Li and Li plus dLi, the probability that you don't move to J would be dLi multiplied by Lj multiplied by wij. So, but this you can write as the differential of wij Li Lj. And this, you can do this for all vertices. Because you can do this for all vertices, you have kind of an exact differential. So you can write the holding probability that you hold on side V on a time interval T1 minus T2 as a difference of that function f of psi as the initial so exponential of minus the difference of so that function at the initial local time configuration and at the end local time configuration. And here the square root of, so you shouldn't have any phi, so there is a mistake. The phi's here should be all equal to 1. But the square root of 1 plus 2L just corresponds to the change of time. So I think it should be actually the square root of 1 plus L, not plus 2L. So it's another typo. So so that's for the computation of the holding probability. So now the computation of the jump probabilities. So you just have to you have some terms like wij again. So you have all the phi's are 1. So square root of 1 plus Lj over 1 plus Li dt. And you multiply them. So actually you will have a telescopic product, but you don't see that telescopic product immediately because you notice that here on the denominator, when you are at I, the denominator changes. So in order to see that telescopic product, you have to introduce, instead of looking at that quantity, 1 plus Li, you look to the power of 1/2, you look at 1 over the product of 1 plus Lj at the power of 1/2. And this, the advantage of that quantity here, Ji, is that it doesn't move. It doesn't change when the process is at I. And then you can write it as a telescopic product because of that remark, and you get the result so that I claim here in that formula. So that will be for today's lecture. So a consequence of that formula for the probability of a path, which depends only on local time and site, is that the process is partially exchangeable. So it's an easy consequence, which was proved by Xiaolin Zhang in a paper where he shows that vertex reinforced jump process in some way is the only simple process which is exchangeable, which is interacting with local time, which is exchangeable. And because of that exchangeability, you can write so that vertex reinforced jump process as a mixture of Markov jump processes with jump rate from I to J, which is 1/2 of Wij e to the uj minus ui, where you take ui as the limit. Sorry, yeah, here there is also a typo. Ui should be the limit of 1/2 of log of Li of t over a certain, let's say, Li0 of t, for instance. or any reference vertex. So, okay, I'll stop here. So next lecture, we'll start by explaining quickly how you can find the limiting measure by the same Bayesian approach. And then we'll go on to discuss the star edge reinforced random walk, the star VRJP, and we'll discuss also the random Schrödinger approach, which enables you in particular, thanks to a paper of Sabo and Zhang, to deal with infinite graphs. Okay, thanks for your attention.
Okay. Thank you.
So do you have any question?
Yeah, so I will
So I had
stop
one
the recording and we can have questions indeed.